skewed W with your both the N behavior, it's like your both hands up, and the polynomial degree, even with even degree. With R degree, you have one hand up, one hand down the graph. All right, let's use calculus idea, right? Let's take the first derivative. So first derivative equals to 4x cubed minus 12x squared. We factor out 4x squared. Then the factor, put in the factor case, 4x squared times x minus 3. And if we set this one equals 0, we get two critical numbers. Right? We set this one to be 0. Oh, okay, it's down there actually. I don't have it right here. It's here. So we set the first derivative equals 0. We obtain 0 and 3 to be two critical numbers. Let's use the second derivative test. So second derivative, take the second derivative. So which is we take the derivative of the derivative function. So get second derivative. So we get 12x squared minus 24x. We factor out 12x, right? Then we have 12x times x minus 2. Then we set this one equal to 0. Set the second derivative equal to 0. Then we get x equals 0, x equals to 2 as the inflection point. Right, let's do here. So let me add one here. So set the second derivative to be 0. We get two inflection points. I'm going to use IP, inflection points. So x equals inflection number, let's call it inflection number, because it's only x value. X equals 0, x equals to 2. Okay. You see, we set the first derivative function to be 0, obtain two critical numbers. 0 and 3 to be critical numbers. We set a second derivative function equals 0. We solve for x, we get two inflection numbers. All right, so those two set of numbers are different. Then, so we have, we want to use second derivative test, right? Second derivative test is saying, okay, derivative to be 0 at 0 and at 3. Now let's evaluate the second derivative at those two numbers, right? The C, let's call this a C. C. So f double prime of 0, let's evaluate the second derivative at 0. So we get 0. Then we evaluate second derivative at 3, we get 36. So 0 is not less than 0, it's not greater than 0. So 0, 0, we cannot see anything. We cannot make any conclusion according to second derivative test, right? Second derivative test is saying either greater than 0 or less than 0. Equal to 0, that means it's an inflection point. Inflection point so 0, 0 is inflection point. It doesn't give you maximum, doesn't give you minimum. You see all those inflection points. This is inflection point B, right? It's in the middle. It's not maximum, not minimum, but it's inflection point. So inflection point is not minimum, it's not maximum. So that's why here, 0, 0 is inflection point. We could see from here, right? Because we solve inflection numbers, we set f double prime equals 0, x equals 0. If x equals 0, f0 equals 0. So 0, 0 is the inflection point. Inflection point is neither maximum nor minimum, except some extreme cases. All right, so f double prime at 3 equals 36, which is greater than 0, right? According to the second derivative test, if it's greater than 0, then it's local minimum. It's local minimum. So that means here, so x value is 3. If x value is 3, f of 3 is a local minimum according to second derivative test. All right, what more can we see here? So we want to sketch the graph, right? So far we have critical numbers, 0 and 3. We can find the critical points. And we have two inflection points, right? 0, f of 0, 2, f of 2. Also, we can separate into intervals, right? From negative infinity up to 0, then from 0 to 2, then from 2 up to positive infinity. We evaluate the second derivative. Right? Second derivative in this interval is positive. That means it's concave up. In this interval is negative. That means concave down. In this interval, again, it's up. So concave is positive. It's concave up. So we can put all those knowledge together. 0, 0 is the inflection point. And then we have a local minimum. So 3, f of 3 is a local minimum. It's easy to evaluate f of 3. So which is a negative 27. So this point is a local minimum. And with the inflection point is 0, 0, right? We have this inflection point. We have another inflection point, 2, f of 2. F of 2 is negative 16. This one as the inflection point. Polynomial degree 4, we know both hands up, right? And we can solve also for roots. We set the original function equals 0, so we see we have two roots. We have x equals 0 and x equals to 4. So 0, 0 is a root. It's a 0 for the function. Also 4, 0, right? We have those 2 points as roots here. And then we can graph, right? We know polynomial degree with the leading term positive. We have this. We have a hands up, both hands up. Then go to 0, 0. That's the inflection point. So concave down. Inflection point change to concave up. Inflection point change concave up to concave down. Then 2, negative 16 is another inflection point. So from concave down, change to concave up. Concave up. It's a really mild curve. Really mild curve. But change to concave up. Then 3, negative 27 is local minimum. It's local minimum, right? The function from decreasing local minimum change to increasing. That's how we use the second derivative test in this kind of graphing skills. Okay, if you have any questions, stop me anytime. Let's see example 6. Sketch the graph for this function. So I have the function is defined as x raised by 2 over 3. So basically this is x squared cubic root. When we have a fraction exponent, the numerator is the power, the denominator is the index, right? Square root of x, the index 2. Cubic root of x, the index is 3. So x raised by 2 over 3 times 6 minus x raised by 1 over 3. 1 over 3 exponent is the same as cubic root of 6 minus x. Okay, so we want to sketch this graph. Let's get as many information as possible, right? We may find roots, y-intercepts. Roots are x-intercepts, right? We can use first derivative, we can use second derivative tests. All right, let's follow this. So let's find the first derivative. we use product rule, right? So product rule is saying take a derivative of the first one. Let's take this one and this one. Think about this as two functions, product of two functions. So take a derivative of the first one. So we get a 2/3 of x raised by -1/3, right? Then multiply by the second term, multiply by 6 minus x raised by 1/3. Then plus multiply the first one, take a derivative of the second one, which is 1/3 of 6 minus x raised by -2/3, then multiply by -1. Simplify from there, get this one. Then we take a derivative of this, right? We may use quotient rule, product rule, then chain rule, all those rules we need to use. Then we get a second derivative. Simplify afterwards, we get this. All right. Let's set the first derivative to be 0. So we want to find critical numbers. We want to find inflection numbers or critical points, inflection points. Set the first derivative to be 0. A fraction to be 0, only the numerator can be 0. Right? The denominator can never be 0. So solve for 4 minus x to be 0, that's x equals 4. So get a one critical number. One critical number, 4. So let's see. Right, 0 is not in the domain. 6 is not in the domain. So we have two vertical asymptotes. Right? 0 is not in the domain of f prime of x. F prime of x. Right? 6 is not in the domain of f prime of x. So what we get? Remember, we get this kind of vertical lines at the point, which means the derivative is not defined. Right? Derivative is not defined. When does the derivative not defined? So we see here x is 0 because f prime of x is not defined. X equals 6 because f prime of 6 is not defined. Not defined. Derivative function is not defined means we get vertical lines at the point. Means the tangent line is vertical. So we get two vertical tangent lines at x equals 0, at x equals 6. And then we have one critical number, 4. So with these three numbers, 0, 4, 6, we can separate the interval into 4 intervals. So we will consider from negative infinity up to 0. What we can represent the interval in this case, x less than 0. That means from negative infinity up to 0. Well, x is in between 0 and 4. Well, we can write as 0, 4. X in between of 4 and 6. We can write as 4, 6. So we want to figure out those factors. So we have 4 minus x, the numerator. In the denominator, we have x raised by 1/3, 6 minus x raised by 2/3, right? Because all we need is to figure out if derivative function is positive or negative. So in the first interval, derivative is negative. We know the function decreases in this interval. Evaluate in the second interval, so we just pick a number, right? So for the first one, we may pick a -1. We may pick a -1 for the first interval. Just pick a representative. We pick -1 for the first interval. For the second interval, maybe we pick 1. Just pick a representative. As long as the number in the interval, it works. For the third one, we can choose 5, right? We can choose 5. Just pick a representative in the interval. The last one, as long as it's greater than 6, maybe we pick 7. Or maybe we pick some easy numbers. Right? Maybe we pick some easy numbers because here we have x raised by 1/3. You can pick maybe 9. Actually 27, maybe 8. Right? Pick an easy number to easily evaluate. But doesn't really matter because all we have to do is figure out is positive or negative, right? 4 minus negative 1 will be positive. Negative 1 raised by 1/3 of negative. Negative here, see, 6 minus negative 1, 6 becomes 7 positive. Okay? All we have to do is to evaluate is positive or negative. We don't need to get an exact number. So the conclusion is this: f increases, f decreases in this interval, then increases. F decreases from negative infinity up to 0. Function decreases. All right, function decreases up to 0. Up to 0. What happens at 0? The tangent line is vertical. So I have a vertical tangent line. A vertical tangent line. Then from 0 to 4, function increases. From 0 to 4, function increases. Right? Then from 4 to 6, function decreases. Function decreases. What happens at x equals 6? Another vertical tangent line. Another vertical tangent line. Right? Then from 6 moment on, function still decreases. So function still decreases. But we don't know how the function wiggles, right? So we need a second derivative. We don't know if it's cup up, cup down, because from here to here, we may draw the graph like concave up, right? From here to here, maybe we could draw the graph concave down like this, right? So we don't know if it's concave up, it's concave down. So we have to use second derivative test. Second derivative. So let's use second derivative test. So second derivative function we find here is negative a divided by this denominator. So let's evaluate at those three numbers, right? At 0, still not defined. We may not evaluate at 0 and at 6. Let's see here. So here is second derivative. So second derivative of the function, and see, this is x raised by 4, right? X raised by 4 divided by 3, but the power of x is 4. So even x is negative, but this term is still positive. This term is still positive. And if x is less than 0, if x is less than 0, so this term is positive, but 6x, so this term is still positive, right? So let's see, we have, so if this term is positive for all x, and then we have the second derivative less than 0 for x less than 0. Why? X less than 0, we have this term positive. Oh, the second, right, because the numerator is negative. Because this term is positive, the denominator is positive, but the numerator is, we have negative 8. So second derivative is negative when x is less than 0. When x is negative. So x is negative, the second derivative is negative. And from 0 to 6, we can choose one representative, right? We choose one representative, which is a positive number. So the first one is a positive number. The second one is a positive number for the both denominators. And again, the numerator is negative. So from 0 to 6, also the second derivative is negative. And so negative means concave down. So if x less than 0 from negative infinity up to 0 is concave down because second derivative is negative. So have this concave down look. Then from 0 to 6, also second derivative is negative. 0 to 6, also concave down. Concave down, also concave down. What happens if x is bigger than 6, right? If it's bigger than 6, we have the denominator, first term in the denominator is positive. The second one will be negative. Numerator is negative, this term is negative, so we get a positive. So that becomes, after 6, becomes concave up. concave up. That's why we have this kind of graph in the end. All right, any questions? Okay, so some of you already did concave up, concave down. So let me give you a couple more. Let's try this. Let's okay, great. Let's try 23. 27, 21, 20, 21, 23, 25, 27. Okay, let's try this 4. So 21 up to 27. Okay, let's try this now. Okay, Noella has a question. Do you want us to focus on part C since it has to do with concavity to all parts of the question? Yeah, let's do all the parts. All right, let's do all parts A, B, C, D. So basically, to graph our end goal is to use the information A, B, C to graph the function, to be able to graph the function. All right. Yeah, Emily, get yourself ready, all right? Let's leave a couple more minutes. So as long as I have 4 people to present, okay, I have 21 claimed, 23 claimed. Oh, right. Emily here. So Emily 21, Ursa 23. Okay, so I have 21, 23. 2 more questions, 25 and 27. Let's wait a little bit. But do get yourself ready if you want to present. Okay, anyone wants to try 25, 27? Okay, let's start with Emily. Emily, are you ready? Great.
Can you see that?
Yeah.
Okay, so for question 21, the function is f of x is equal to x cubed minus 12x plus 2. So to find the interval which it increases or decreases in the local maximum, I took the first derivative, which is equal to 3x squared minus 12. And then I put that equal to 0, which I got x is equal to 0, 2, and negative 2. I did a sign line test, which I test on whether or not the slope was increasing or decreasing. So I took numbers that are less than negative 2, in between negative 2 and 0, 0 and 2, and numbers that are greater than 2. Below is like the work I showed for negative 3, negative 1, 1, and 4. Through that, I found out that f increases on the interval of negative infinity, f increases on negative infinity to negative 2, and 2 to positive infinity. And f decreases on negative 2 to 2. The local maximum is at x is equal to negative 2. Oh, what happened?
I'm sorry, something happened. Can you give?
Oh,
You guys see my work now?
yeah.
Okay, so local maximum is at x is equal to negative 2, which I plug in that number to the original function to get the point negative 2 comma 18. And then local minimum is at x is equal to 2, and in the original function, this point is at 2 comma 14. These are the work for part A and B. As for part C and D, to find the concavity in the point of inflection, I took the second derivative, which got me f prime x is equal to 6x. And then that equal to 0 gives me the point of x is equal to 0. And then I did another line test to test that numbers less than 0, the function concaves down. And when numbers are greater than 0, it concaves up, giving us the point of inflection at x is equal to 0. And as I wrote right here as well, f concaves down from negative infinity to 0, and it concaves up from 0 to positive infinity. And then this is the graph I drew. At x is equal to negative 2, it's the maximum point. At x is equal to positive 2, it is the minimum point. And then at 0, there's this shift between concave down to concave up. So that's the point of inflection.
Great. So how do you know the n behavior like this?
Well, it's a third degree polynomial, so it like sort of like curves around the point of inflection, and then third degree is an odd function, so the n behavior goes opposite directions.
Right, right. And the leading term is positive, so you know it's like a right-hand side goes up,
Yes.
left-hand side goes down. Yeah, great. Beautiful work. Thank you, Emily.
Yep, thank you.
Okay, Ursa. All right. Yeah, you may present the next class. All right. So I have like 14 minutes. Maybe I'll talk about optimization. So I'm going to skip this curve sketching. Well, let's just go through this. All right. So how to graph. So far we have all those tools help us to graph, right? We know how to give us any function. We can find the x-intercept, right? We can find the y-intercept. We can find the domain. We can find the vertical asymptotes, horizontal asymptotes. Asymptotes. We can find out the intervals of the function increases or decreases. We can find the local minimum, local maximum. We can even find out if the graph in the interval is concave up or concave down. So we know all this, right? We have all those tools at hand, so we know how to we can sketch a curve or we can sketch a function. So I'm going to skip this. This basically is like a summary for all the skills we have learned. So I'm going to focus on optimization. Okay, this is 3.5. It's a very important concept. Optimization problem. So in life, we want to minimize cost. We want to maximize profits. Things like that. So in life, we have a lot of optimization problems. Okay, so you may read these steps yourself. All right. Let's see the first example. So basically, so this section is to use all the strategies we have learned. So let's see. This is life applications. Example 1. A farmer has 2,400 feet of fencing, right? And wants to fence off a rectangular field that borders a street river. He needs no fence along the river. So what are the dimensions of the field that has the largest area? So this is the question. So basically the question is asking, what's the best dimension we could have to have the biggest area, right? So let's see some scenarios, right? So totally he has a 2,400 feet, the parameter for 3 sides. So along the river side, there's no need of fencing. We need to fence off 3 sides of the rectangle area. One situation could be, the width be 100, 100, the length is 2,200, which adds up to 2,400. Or we could have 700, 700, 1,000, that adds up to 2,400 also. Or 1,000, 1,000 plus 400, right? It adds up to 2,400 also for the parameter of 3 sides. But which one gives the biggest area? Or maybe there are a lot of situations, right? Which one gives the biggest area? Let's see these 3. So the first one will give us this much, right? 220,000 square feet. The second one gives us 700,000. Then 400,000. Well, in this case, it's 700. By trying an arrow, this is 700,000. But this might not be the biggest area, right? Just out of these 3, this is the biggest. So how do we solve this problem? Think about it, right? Think about this may be a function, right? Think about, we have to come up with a function. We want to use the idea or largest area, right? Largest area. So maybe we want to make a function of area. Then, if it's the largest, that means they give us the maximum point. And if we have a function, we know exactly how to find the maximum point. So that's the idea. So first, we need to work with a function. Because this is regarding to the area, so we better start with an area, right? So what is an area for any rectangle? Area equals the length times width, right? Let's call the length y. Let's call the width x. So the area equals to width times length. But we want to have a function. This is not a function. Or you can see A is a function of 2 variables, x comma y. It depends on both variables. But we want to have a function of a single variable. So we want to reduce one of these variables. We want to have maybe A of x, right? So how do we, starting from here, get A of x, right? only a single variable function, and then we know take derivative, set to 0, find the critical numbers, right? Then maybe use a second derivative test to find a local maximum or local minimum. So how do we reduce these two variables into one variable? Well, we have something to use, right? We're told the parameter of the three sides is 2,400 feet. So that means with this picture, we have x plus y plus x is constrained to be 2,400. So 2x plus y is 2,400. We can solve y. So y equals to 2,400 minus 2x. Right? Now we substitute y into the area formula. So x times y becomes x times 2,400 minus 2x. So this, we made a function. We have a function of a, area A, only depends on x. And this is downward parabola, right? We say this is downward parabola. Downward parabola gives us a maximum. Okay, so we made a function, area function in terms of x, the width. And now we want to take a derivative. So we take a derivative of this function, a prime of x equals to 2,400 minus 4x. We set this derivative to be 0. We solve for x. So x equals to 600. Right? 600. We know this is a quadratic function. We don't have to do furthermore, right? Quadratic function only has this downward parabola because the leading term is negative. The leading term is negative, we have downward parabola. And the derivative equals 0, we only have this 1 point maximum. And you know, so the width is 600. We can find the length. Y equals to 2,400 minus 2x. So y equals to 2,400 minus 2 times 600, that's 1,200. So that equals 1,200. And then that's it, we finished. The width is 600, the length is 1,200. So the picture here, so we have this is 600, 600, 1,200. In that dimension, because the question is asking us the dimension. What are the dimensions? It means what is the width, what is the length? So that here is our answer. Width 600, length 1,200 will give us the largest area. And then that's it. That's for this example, right? So that's the rectangular field should be 600 feet deep and 1,200 feet wide. Let's see example 2. A cylindrical can like this is to be made to hold 1 liter of oil. Okay, 1 liter of oil to hold. What's that? That's a volume, right? That's talking about the volume of this cylindrical can. So find the dimensions. Again, find the dimensions. What are the dimensions of a cylindrical can? We have a circle for the top, for the bottom and the top. So a circle is defined by the radius. So this is one dimension. One dimension is the radius of the circle. And another dimension is the height, right? Height. So the radius of R and the height of this can are the dimensions of this cylindrical can. So we want to find the dimensions of this cylindrical can. We'll minimize the cost of the metal to manufacture the can. All right, so how do we make a can out of metal? We have the bottom circle, we have the top circle, right? And we have the body. The body, if we slide, we slice from a point, we see the body is a rectangle, right? If we cut in the middle, then we make it flat, that's a rectangle. One dimension is the height, Another dimension is the circumference of the circle. So circumference of the circle is 2 pi r. So this is talking about the area, right? So one way we want to, so we have the volume, right? The volume is given, hold 1 liter, and we want to find out the area, the minimum area, right? So minimum the cost. The more material we use, the more money, right? We want to use the minimum material. So which means we want to minimize the surface area. The surface area of this cylindrical can. The surface area is made by 2 circles and the body, the material for the body. The material for the body, if we cut somewhere, we make it flat, that's a rectangle. With one dimension is the height of the can, another dimension is the circumference of the circle. Circumference of the circle. Okay, now, so let's see the area. Let's try to make the function area function. So the area, surface area equals to 2 circle, 2 pi r squared, plus 2 pi r times h, right? Top and bottom and the body. So that's the area. Here we have r and h. We have 2 variables. Right? We want to minimize it to be a single variable function. How do we do that? We want to use the volume. The volume is fixed. The volume is fixed. That means the r and h has a certain relationship. So what is the volume formula for this? It's pi r squared times h. So the volume equals 1 liter, which 1 liter is 1,000 centimeters. And the volume is pi r squared h. So pi r squared h equals 1,000. Now let's solve for h. So h equals to 1,000 divided by pi r squared. Then let's substitute this h into the area formula. So I have 2 pi r squared plus 2 pi r times h. Now we are able to make a function in terms of r. This function is a rational function, right? It's a rational function, see here. Or it's polynomial-like. So made a function in terms of r. So the area of this cylindrical can depends on the radius of the circle. So we have this function. Let's take derivative, right? Derivative, once we take a derivative, set to 0, we'll be able to find the maximum minimum. Right? Solve for critical point first. So derivative of this function, we have 4 pi r. Then remember, this is r raised by -1, right? We get a negative 2,000 divided by r squared. Combining those two terms, we have 4 pi r cubed minus 2,000. Then the 4 is common factor, so we can factor out. So the derivative function is this. Now we set this one to be 0. We set derivative function to be 0. Let's try to solve for r. Then we solve for r, so we get r equals to cubic root of 500 divided by pi. Right? Pi r cubed equals to 500, so r equals to cubic root, so 3 is the index. Cubic root of 500 divided by pi. And that's it. Once we have r, we can go back to solve for h, right? Plug it into this equation. We solve for h. And then now we find the dimension. So the dimension to minimize the cost of the material is the radius is this, and the height h is this, which is 2r. And that's it. All right, this is how we use the first derivative set to be 0 in real life. All right, let me quickly give you some questions to practice for next class. Okay, 2. 2, 4. No, you know what? Let me do this. 2 to 4. 7, 8. 7 to 9. All right, let's try those 6. All right, any questions? Can you leave more problems? Are we also doing problem from before? Yeah, I left 21, 20. So Emily showed 21, right? We still have 23, 25, 27. And also for this one, practice on this optimization. All right, it's an important concept. So 6 plus 3 more, 9 questions in total. I think that's enough because you still have homework to do. All right, have a good day. Thank you, thank you, thank you. I'll see you next Monday, right?